Start recording. Yeah, I
Sharing
think it's
screen.
recording now. Yeah.
Oh,
So
you
it's,
disabled screen sharing.
oh, yeah. Hold on one second. Um, okay, try now. Cool.
All right, cool. So,
So you
uh,
just basically imported you didn't have to change it at all, the file. You just put it into Colab.
yeah, I just opened it in Colab.
Okay,
Every cell, like I went through it, and every cell worked except for the last one, which we'll figure out what's going on with it.
got it.
Um, but I went through all the links, so we can start at the top. So, this Markdown sheet link goes to this page, which is basically like a general tutorial on like how you would want to mark down your notebooks for when you want to do uh like structural changes similar to like latex. So whenever you want to do like headers, if you want to do uh so you'll see like all the examples, and you can run through this on your own time,
Mhm.
um for when you want to like have a polished notebook that you plan on distributing to other people. But it also has like important things like links when you want to display links, uh, like tables, lists, like facts and figures, that sort of thing. You can also have in-style images. You can also like you'll be able to do like codes and syntax highlighting. So that just means like small like code gists, or if you want to do like that sort of highlighting like you see inline.
Mhm.
You can put in native like HTML code if you want to display like uh, set up like I don't know, block things out or whatnot. But basically, like you can see that there's like just like a bunch of different things you can do to make your like notebook a lot cleaner.
Mhm.
Yeah. So here's like so like here's the HTML. So you can do like native HTML and just display like lists, or if you want to display like tables or anything, you can do it the programmatic way.
So
Um,
you don't have to like declare that you're writing in HTML. It's just you just
no,
start.
yeah,
Okay.
it gets interpreted by itself. So uh, if I want to insert like a table, I can just put a table div in, and then it'll actually structure it the way I want to.
Let me see.
Um, I don't know if there's markdowns, like CSS related markdowns for these tables. I'm not sure. I'll need to look into it. But you can actually even embed like YouTube videos if you
Hmm.
want.
This is
Which
interesting.
Yeah, so there's a lot you can do for your Python notebooks. Usually you'll want to hold like what I tend to do is actually have two notebooks for any project I'm working on. One that's going to be my fully polished one that I end up distributing to other people, and one that's more of my experimental one where I don't really worry about markup, and then run very like different types of experiments. That one looks more like a long running kind of notebook, and then when you're finished with like when you finally got all the results and everything, and you know which blocks of code you want to import into the final thing, I just tend to move over every like the pieces one at a time, do the markup, and then the write up for it, and then continue.
Okay. So I have a question, not about like the markup per se, but about like how GitHub might play into all this.
Yeah.
So I'm assuming that you can like somehow locally like pull your GitHub onto your computer
Oh yeah.
and then like upload it back on using like
Yeah.
Git, right? I think.
Yeah. So this is actually something if I planned on having in the document. But basically, what you want to do is any project can be linked. So any project you write locally, you can link into your GitHub account.
Okay.
And so what you would do is just like you can either do that manually, or if you want to avoid like manually meaning by command line and using Git. If you want to actually avoid that, you can download Git Desktop for Windows or Mac,
Hmm.
which is like a GUI interface for linking your projects from GitHub directly to your local versions on your site. And then depending on which kind of code editor you use, um, you can actually link all three of those things together. So the online version of your Git account, and then the actual project repo, you can link that to your GitHub desktop app, and then and then that acts as like it acts as a centralized repo locally for all your projects that you have on your computer. And then you can add whenever you work on it locally, you can set up your like project repo, or like you can set up your code environment to then like merge and push requests, or push like any changes, or download any new changes directly to. So I actually, instead of me like trying to explain, I can actually just show you. So GitHub desktop should open in a sec. Yeah. So
Okay,
GitHub.
so I think you might only be sharing your browser screen, so you might need to share like your whole screen.
Oh yeah. Okay.
'Cause I can only still see the browser.
Yeah. Give me a sec. Hold on. I'm trying to figure out why. I think I minimized the. I think I need to pause screen sharing.
Yeah.
Okay, cool. Hold on. Let me try again. Where's GitHub desktop? Okay, here we go.
Okay.
Cool. So yeah, so this is what GitHub desktop looks like. And
Okay.
basically what it's doing is it's pulling, you can set up and add repos that you have already set onto your like local GitHub. And then it links the two together. So this is going from like your local version directly to the repo that you have in your account.
Hmm.
And then what you can do is, if you use a code editor like I use Visual Studios, or if you use like Atom or Sublime or whatever,
Mhm.
there's packages you install that allow you to sync your GitHub repo directly to your code editor. So that would
Hmm.
basically mean that as soon as you finish, a task or whatever, you just need to write you just click that you want to commit a new commit, like commit a new change to your repo. You write the little message out, add all the files, and then just push it manually. So it's just a button. Usually it looks like an arrow.
Mhm.
And then you can push it to whatever branch you're working out of. This GitHub desktop in turn notices that there are changes, and then pushes those changes to your GitHub like repo in your account. So it keeps everything in sync and current. This kind of acts as like your centralized like GUI for any changes that happen, or all your repos basically locally.
Okay.
So when you work on a notebook, for example, you just like work on it locally. Whenever you're done making changes, you would just write a commit and then push your commit
And
through the code.
you can save those changes in the Jupyter notebook itself, right? Like.
Right. So but in the Jupyter notebook, when you're doing a save, if you change anything and you just do a save, you're saving it locally.
Mhm.
So if you wanted to reflect that in GitHub, you'll need to push your change, like the new changes.
Mhm.
So it's a two-step process if you want to see it like changed in your GitHub account,
I see.
which you can either do via command line, which is usually just like git -m and then the message, and then git add all the file names that you want to do, and then finally git push
Okay.
to the, and you'll need to set up like the first, like there's a setup institute, like a setup tutorial on GitHub site. So for the first time, like if you haven't used Git before,
Mhm.
which I can send you, so that'll help. Um,
Okay.
yeah, so that's that. But GitHub Desktop's really helpful, so I would definitely, I'd probably download it because it lets you switch between like whatever project you're working on. If you work on multiple projects at the same time, it just helps you like keep everything set up.
Okay.
Like, yeah. All right. Now that that's good, I'm gonna go back to the Where is it? Cool. Yeah. Okay. So after the markdown, so in Google, like in Google Colab, when you write these like notebooks, all you have to do is just hit the plus button, um, and it's already up. Like after you run a cell, like you would see a number next to it, which just tells you the order in which you've run cells. So if you say like, usually you would write like a notebook to be continuous, like so you do like step one, then step two, then step three, or whatever. But sometimes you write notebooks where you're writing it like module by module, and the modules don't interact with each other. So like, say I want to have like, um, even like this could have been written as like is kind of written like modules.
Yeah, yeah, yeah.
Um, so
I kind of get what you mean. Yeah.
yeah. So Python lists versus NumPy arrays. If you look at most data science applications, you're using NumPy arrays for pretty much everything. This is more of an efficiency related issue. So you can look at the link.
Okay.
But basically what it's doing is that the internal representation of a list element in like the original Python package like is a lot less like efficient on memory than NumPy arrays. So NumPy arrays are beneficial because there is like the number of bits you need to store a list of numbers is only 96 times the number of numbers you're trying to set. I wasn't sure actually why it's that specific value, but for the list, it's not, it actually is copying references to the number in addition to storing the number. So the total amount of memory that it's using is like 28 times n plus like 8 times n or something like that. So it's like, or 28 times the length of the list, 28 bits times the length of the list plus 8 bits for every times the number of numbers you're trying to store in that list. It ends up, for very large numbers, it's significantly worse on memory and speed, like Python lists. So we use NumPy arrays for everything. So if you look at like pandas or other like popular data science packages, they all use NumPy arrays. And that's just for the like efficiency purposes. However, if you actually, so like when you look at this, I just ran this cell. So if you look at here, what we're doing is just printing out Python list and Python and like NumPy array. You'll know it's a NumPy array if it has a prefix array and then parentheses the list.
Okay.
We'll talk about vectors. Yeah, so NP, like again, it's just easy. Like this is how you would syntactically just create a NumPy array for, or not a NumPy array, like a NumPy vector. There's various like matrix or vector operations. So you can do sum, mean, standard deviation, dot products. I think there are more operations, so you can check in the, I think it's the NumPy homepage, like their official project page. They have documented like an API guide, so you can see like there's a lot of different types of like functions that you can call additional, like in addition to these, but these are the like default ones. Oh wait, I should run these too.
I think they're already run.
No, they would only be run if they're only run if you have a number next to it. So if you see like,
Oh, I see.
yeah, when they're blank, you haven't run the cell. This is from like the last,
Oh, I see.
yeah, instance of running it, which is fine. But sometimes like if you have a vector x and you define a vector x and you run the cell, and then the next thing you're doing is calculating the standard deviation of x, but you'll need to run the first cell first because it actually defines or creates an instance of x, and then when you run the next cell, then you would get the correct number. But say I spin up this repo again, and then run just the standard deviation of x, it wouldn't know what x is because I didn't run the prior cell.
Got it.
Yeah, so you're calculating the mean. Other things that you might want to keep in mind is that a lot of these values, like using NP mean or NP standard deviation, default to floats, which sometimes is not what you want. Sometimes you want whole number integers. So like, for example, representing images, when you do calculations on images, you don't want fractions of pixels. All right,
Oh
matrices.
wait,
So yeah,
sorry, I missed that. So you were saying something about like so they default, some of them default to integers and some of them default to floats. Is that what you're saying?
yeah. So if you look at these, like np.mean, for example, displayed 2.0. So
Yeah.
that's a float, um, and standard deviation is calculating the float. Dot
Hmm.
product, I'm not sure if it defaults to a float or if
It
you
looks like
did
an
like,
integer.
I'm not sure actually if this defaults to float. It might be dependent on what you're multiplying, like the
Well, if
original
it was
values
float, it
against.
would be 28.0, right?
Right, but what I mean is like x and y themselves may have been like one, like whole number integers. Like if you did an integer, if x only contained integers and y only contained integers, and I do a
Hmm.
dot product and it returns me an integer, or if it's,
Oh, I see.
yeah, so, or if I did float by like a float times a float and still got
Hmm.
an int.
Hmm.
Um,
Hmm.
I would check the NumPy documentation to be specifically sure, but there are times where the representation, the output representation actually does matter depending on your use case. So for example, if I'm doing some sort of filtering on pixels, my original image will likely be grayscale or RGB values, but they usually are between 0 and 255. So I wouldn't necessarily want fractional values for
Hmm.
that. That could cause blurring or whatever. Um,
Hmm.
yeah, so I would be like, I would always try to make sure what output, like what format it outputs in. Additionally, some of these like commands later on also only accept like certain types. So you would want to make sure. We'll get to that. So matrix creation is really easy. You just call np.array, and then you just, depending on how large your array is going to be, all you'll do is just just write down the row and then commas between rows, and that will generate a 3 by 3 array, for example. Yeah, okay. So here's like np.ones, right? So this basically is just creating a ones matrix, and you just define like the number of rows you want and the number of columns. And you can see here, like you just called np.ones, but it actually is outputting floats. It did one
Oh,
dot,
okay.
1 point dot. So
Okay.
uh, I think there are flags. I think it's in the documentation, but they have these flags that you can apply to basic operations like ones or zeros, um, like np.ones or np.zeros, that allow you to select uh, which type the integer output should be. So this
Hmm.
defaults to float, but I think you could impose whatever type it should be. So you could probably make it an int. I think it's a I think the flag is called like d type equals, and then you can put in like float or int or whatever. But I think it defaults to float.
If it was type equals, how would you type that in? Would you like type that line and then do b dot type or something like that?
Yeah. Let me actually. I'm gonna stop sharing for a second. Hold on.
I'm just curious. I mean, I could look it up also, but
NP.
I was just trying to see if you already knew.
Yeah. See, I don't know. I've seen like not for this specific, like not for np.ones, but I have seen that you can do like d type and then set an equals and then determine what you want as the output.
Let's see.
One sec. Yeah. Okay. That's okay. So yeah, you can. Yeah. Okay. So here, let me screen share for a second. Yeah. So actually, yeah. So this is the parameter I was talking about.
Oh, okay. So it's just a
Yeah. So
parameter. Okay.
okay. Add. Anyways, yeah. D type. So it defaults to a float, but you can, for example, put int. So if
Uh-huh.
we go back to, I should have went to the original, the official documentation page. There's just so many ads. Okay. Let me switch over. That's not what I'm looking for. Okay, do you see Google Colab there?
Yeah, I see it.
Okay, cool. Yeah, so np.ones is a tuple that represents its, oh yeah, okay, so it has like,
It's references, yeah.
yeah, which is nice. So you could do dtype and then set it equal to int, and then run that, and you should get ones. Yeah.
Yeah. Okay. Cool.
Yep. So np.random is basically there's a random package within the NumPy package itself that
Mm,
allows you to select random numbers between whatever you want. Um, this is actually just determined. It'll always default to 0 to 1, like values from 0 to 1. This random number is this is like let me, yeah. So you can pick the size. So this is what that, like, the 3x3 tuple is just dimensions.
mm-hmm.
There's a difference between np.random and then np.sysrandom. So this random is not actually truly random. There is basically, I don't actually, okay, so I know that like this random isn't quite as it's pseudo random. If you wanted like a really, really random, you use like np.sysrandom, which is
Okay.
using your system, like your system CPU to generate random numbers. It purposefully purposely injects randomness into each calculation. So a lot of people, when you have like something that you need like truly random numbers for, you usually use np.sysrandom.
Okay.
But I think this is like acceptable for most use cases.
But it's always NPRD.
No, okay, yeah, that there's, okay, so that'll, let me clear that up. So you can install, so you're basically importing a sub package from the NumPy package. Like you don't
Mm,
necessarily need the whole thing. So to
I see.
simplify like your like code, you're basically like you're importing numpy.random as np.rd. You could even write, like, if you just wanted to write the whole thing out, you wouldn't even need this import statement at the top, and just say numpy, like np dot, and then call random dot, and then the thing.
Oh, okay.
This is like creating an alias or things.
Yeah, I got it.
Yeah.
Okay, that's cool.
Yeah. Okay. Did I hide this? No. Okay, cool. Matrix operations you'll probably need. Cool. We got array A, which we already defined before above. So it's using the
Mm-hmm.
same exact A that we previously defined.
Mm-hmm.
Whenever you want to take the transpose of a matrix, it's just A dot transpose, or matrix dot transpose. Same for creating the inverse. Again, you see np.la, which is np.linear algebra. It's the
Mm-hmm.
sub package. And so what you're doing is basically just using the inverse from that. We defined np.la the same way we just did np.rd, or
Mm-hmm.
np.rd for a numpy.random. And then you can calculate the inverse of that same package, or the inverse of that same array of matrix. Oh yeah, okay, so R is the random. Here's one that's really important. You'll probably use it like in everything, like almost every like data science like related problem. Reshape. So reshape basically is just reshaping your matrix into these specific dimensions. So if I wanted to like display, I've reshaped X. X used to be, what was X? Define
This
X.
would be like a 1x3 or something. Yeah, it's an array of
Yeah,
1x3.
right. And now we've turned it into a 3x1. So if I want to show you, like, if you want to see what X is actually like, you can just run X. And so now you see it's a column vector.
Mm-hmm.
And when you want to see shape, you just do like X dot shape.
Yeah, it's kind
Shape
of
is a,
like JavaScript.
yeah. So certain things are properties of, like, inherently are properties of matrices or vectors,
Yeah.
while other things are functions of that. So you're like reshape, you're applying a function to, you're applying a transformation to X, but the shape of X is inherent to a matrix or like a vector.
Yeah. So it's basically saving it like as like 3 arrays, basically, of like
Right.
one value in each array.
Well, okay, so NumPy NumPy arrays are efficient in that like the actual like class structure of like the actual like structure of um, a NumPy array contains metadata about the dimensions of your array. So it has like it's efficient in that it just pulls that value, like it doesn't have a lookup,
Yeah.
which is why it's X is able to be a property. But if you were to say a list object, which is effectively the same representation of an NumPy array, uh, and tried to do like a list dot shape, you would return an error because shape is not a property of a list. But yeah, there's a lot of times where you'll be doing transformations on set data sets where you will need to reshape your data set to be able to do the transformation or the calculation or whatever. So reshape
Mm.
is one that you'll actually want to go read the documentation on because you'll find it useful. Here's the dot product between R, the random matrix R that we inverted, and X. And this one is the element-wise multiplication.
So how do you do element-wise multiplication? Oh, I get it. I get it. So
Yeah,
each x is going to be multiplied by each column of R.
yeah.
Okay.
And then this one's the dot product.
Yeah.
Or dot.
So I also read that you can use at. So if you just did like R at X, it'll do the same thing. The at sign.
Oh, I didn't know that. Let's try it.
Yeah.
Okay, this no R dot or R at is actually
The
uh,
dot. Yeah.
that's the dot
That's
product.
what I'm
Yeah.
talking about. Yeah.
Okay.
There's like 4 ways to do that. It's a little strange.
I didn't know that. I didn't know that. So is there a? Do you know if there's like a performance difference, or is it just purely syntactical?
I
I don't know.
I don't know. Yeah, but I was reading like intro to like NumPy for MATLAB users, and usually MATLAB defaults like this syntax to like a matrix multiplication, or like basically what you have as your dot there.
Yeah.
And so I think they're trying to like make it as easy as possible, and so they just use that as, I mean, it's less cumbersome, right? If you just write
Yeah.
the at instead of the dot x.
All right. Cool. So let's go into what's a kernel.
Okay.
I'm gonna go ahead and open this link.
Okay.
Oh, it opened it twice. Yeah. So image kernels. Um, I should have read. I think I didn't end up reading this link. Kev, do you got like a simple explanation of what a kernel is? It's just like a like a matrix of numbers, right?
That makes sense.
I mean,
And it represents the grayscale value of each pixel in the image.
pretty
I
much.
mean,
At least in,
that's sorry, I just woke up. But so could you go down to there, right? With those, yeah. Um, so yeah, you're correct. The image is represented in terms of values between, what is it, 1 and 256, or no, it's 1 and 255.
or 0 and 255.
Right, which represents pretty much the color of each pixel, either in if it's grayscale, then it's just one value. If it's in color, then it's 3 values for red, green, blue. However, the kernel is that 3 by 3 matrix in the middle. So
Oh, okay.
often in image processing, you want to change the image. And like there's many different kernels. The kernel is what you apply to this image in order to alter the image. Either if you want to like sharpen it, or if you want to blur it, or if you want to calculate the gradient across the image. There's a lot of reasons to have kernels. There's Gaussian kernels. If you want to apply a Gaussian sort of blur to it, but the way that works is that you see, so there's the 3 by 3 matrix, and then you essentially, it's called convolving, or
Mm-hmm.
basically applying that kernel to every pixel.
Mm-hmm.
When you apply that kernel to every pixel, it looks at the 3 by 3 array of pixels around that pixel to calculate what that new value of that pixel is going to be.
Yeah. So it does a convolution operation.
Yeah.
Right. So if you're aware of what that is, that's what convolving is, and it's very important in computer vision and any machine learning tasks that involve images usually.
Yeah, that makes sense. All right, cool.
Cool.
All right, so we're going to import SciPy. And ascent is displayed here, which it looks like it's, I think there was a definition for this. Oh, actually, no, I know what this is. Ascent is just it's a grayscale image. So you can see like the shape of the image is 512 by 512. And then ascent.max will tell you what the max pixel value is in the image. So there's like a pixel in this matrix that has 255 as its max value.
Where did they get ascent from? Is that like, was that imported somewhere, or
Yeah. So
is that a part of SciPy?
It's a part of SciPy.
Okay.
So yeah, if you see like ascent, it's SciPy.ascent or SciPy.miscellaneous.ascent.
Okay.
Cool. So then we import matplotlib. So that's just a basic like graphing library.
Okay.
And it's pretty much like ubiquitous across like all data science. You almost always see matplotlib. And you use it to either display your figures or your graphs or images or whatever. So if you see like here, we've done another alias for matplotlib, but this is just for pyplot, which is just plotting only. So you can see like, you can change it to be a fully gray image, which just normalizes all the values to be grayscale. And then you'll always call image show, like plt.imshow first, and then the thing you're trying to show, and then plt.show actually pops up the value. So similar in MATLAB, how like you can try to plot something, but you have to call figure, or I think that was the command. You call like
Yeah,
figure
it's like plot.
to actually have it pop up.
Yeah.
It works the same way there. Okay, here's what we were talking about earlier in that tab. So to do a blur, you're basically doing a convolution of the pixel in question, as well as its neighbors, 8 of its neighbors. So here what we're doing is basically you're creating a 1x1 matrix, like a 7x7 matrix of ones, and it's being represented as a float, a 32-bit float. And then you're dividing each value by 49.
To normalize it.
To normalize it, yeah. And here's the array of normalized values.
Got it.
Here we got ascent.shape. So this is basically just storing the dimensions, the rows and columns of the original image ascent. And then you're creating a zeros matrix with those same dimensions that will represent the transformed value. And then here's a simple like double for loop to go through each image, and you're basically just calculating the value of this is not the convolution.
Yeah, this is the convolution operation.
Yeah. And so now you can do image.blurred and then image.show. So this doesn't look that much more blurred, but it is blurred compared to the original image, which is a lot sharper. So you can see that they applied the filter.
Okay.
Cool. So matplotlib, we're again importing PLT. So there's a lot of additional types of like plots that you can do in matplotlib. When we end up wanting to have more like when we want more rich visualizations, you usually switch over from matplotlib to something like Seaborn, which tends to build more like visually rich, like figures and plots or whatever, you can do like animations in Seaborn. Um, so usually that's when you want like you'll use that sort of library when you have like a really large amount of data and some really interesting visualization you want to do. But for now, like most of our like simple use cases, we would just use Matplotlib.
I have a question.
So yeah, you can do like scatter plots. Again, you're just creating a random, like 1,000 random values.
If you wanted to save the plots from a Jupyter notebook, how would you do that?
Just there's commands for doing that too.
You could just write in Python.
Okay, the command.
Yeah, I mean, all you have to do is basically like save, instead of plotting the value as like plt.scatter, you just equate it to a variable, and then you can output write it to a file, and then just like there's like a library you can import for in Python that lets you just like write out a file.
Okay, and then you probably specify the
path
type.
director. Yeah.
Okay, got it.
You can do histograms.
Terrible histogram.
Yep. So you can just specify how many bins you want, which would just be how many different like sub like categories you want. So we've chosen 4 for this example.
Well, that's a lot easier than MATLAB histograms.
Yeah, there's not a lot of work in for this compared to MATLAB.
There can be a lot of work. It depends on what you're trying to do.
Oh, true. Yeah. I mean, if you're doing like overlaying like different types of histograms and you want a specific image, that could be a lot of work. Linspace is the same exact thing as MATLAB. So just creating a vector from 0 to 10 with 100 partitions. Here's how you plot like if you want to plot like 2 different things on the same graph, all you got to do is call plot multiple times with the different values, and then just hit show, and it'll do it. So
no hold on.
No hold on. Just do it. If you want like subfigures, like if you want to display like multiple graphs of the same, or like multiple different graphs, but as they're independent figures, you can do subplot. And then you just have to, similar to how like MATLAB worked, where you designate like its position. So you could do like 1, 2, 2, and that'll be the first of 2 or whatever figures in like a 2 by 2 grid.
Got it.
Yeah. Line points. This is the same thing as MATLAB as well, where you just do the plot and then designate what your marker should be. So in this case, you picked 0 dashes connected by dashes. Other times you could do like x's like x comma dash, or x and then a dash to connect them. Yeah. Bar graphs. New bar graphs.
Oh yeah, those look terrible.
Yeah. Cool. Probability distributions. You got all the different ones. Uniform distribution.
Oh, it's built in?
Oh yeah. Everything you want is built in, which is super nice. All the distributions you could need is pretty much built in. So you build, here's 1,000 samples between 0 and 1.
Wow.
And then you can plot here's the histogram, or the numerical value for the histograms. And then here's the actual histogram itself using 1,000 samples.
Wow.
Yep. It's
Wait,
really
so what is that doing? It's simulating.
Yeah, so what this is actually doing is it's creating a histogram, and then you're choosing, it's using x, which is you've called x as a vector that, or a matrix between 0, where every value is between 0 and 1. And there are 1,000 samples of that.
And then it's getting a random value based on a uniform distribution?
Exactly, yeah. And the way this actually calculates that,
or I guess not a random value, right? Then it's, yeah, I guess. Oh, yeah, go ahead.
Yeah, no, this is a random value, like selected between 0 and 1. It's using the random module from like numpy.random. So it's kind of pseudo-random. But the histogram itself is plotting that vector X, or that matrix X, using 100 buckets. So it's partitioned from 0 to 1 by like 100 subgroups.
Okay.
And then you're getting the frequency of all of those subgroups here.
Okay.
Yeah.
I see.
You can do binomial distributions.
Okay.
So if you look here, you're doing the same thing where it's a binomial distribution. You've gone between 10 and 0.7, which is kind of weird. And then 10,000 values of that.
Look at that central limit theorem at play.
Yeah, he's not wrong. So yeah, here you've got a binomial distribution centered around 7, it looks like. And you've broken it up into 10 subgroups. We've got the Gaussian distribution, which is basically just creating exactly the same thing. It's just following the normal 68, 95, 99.7 rule. Oh, okay. This is basically just saying that. Is that like what? Like all the values falling between 2 standard deviations, it looks like. Or 3 standard deviations of the mean?
Yeah, 1, 2. Yeah, 1 is 68, 2 is 95, and 3 is 99.
Cool. So you got, again, it's using that same X that is the Gaussian distribution or the normal, and then you're displaying 20 blocks, buckets of it. Covariance matrix, if you want to do 2-dimensional Gaussian. Okay, so this actually, you're just like selecting, or if you already have your mean and your covariance, you can create the matrix yourself. And then instead of using the normal and like np random dot normal, you'll use the multivariate normal. And then you'll just do the mean, covariance, and then the number of samples.
Wow,
that you
dude. Yeah, it's like optimized for this stuff.
It is. It's super nice. So if you have to do it, it saves you quite a lot of time.
Yeah.
Did I run it? Yeah, okay. And then you can just plot it. So we're taking X and Y and plotting, and you get a nice straight line. Okay, estimating parameters from samples. So this is, if I remember correctly, isn't this the thing we just did in the problem set that was like, if you have a subsample of values and you don't actually know what the distribution is, this is like how you figure out the distribution from your small sample of parameters. What was that called? Okay, I might just be off. No, forget it.
I'm not sure yet.
That is true?
I don't know. You'd have to scroll down more. I don't know what they're doing.
Oh, okay. Yeah, so here you're just calculating the mean based on the normal distribution, and then the standard deviation. And so now you're plotting, or they print out the standard deviation and the mean. Here you're building it looks like you're building a histogram. Okay, there is an error. Rectangle has no property norm, which might mean that they've changed the package. So I think, where is this error coming from?
Rectangle. It's from plot.hist normed equals true.
Okay. Let me see if I'm gonna switch over to plot. That's SciPy. Normed equals none, so technically this should be valid. Is it missing something like a?
Well, let's see if you can write in true. Can you write in true, or what was the value that you have to have?
No, it doesn't need to be normed.
No, what I'm saying is
Oh, okay, here we go. It just tells you what. Oh, it says range equals none.
There is no normed. It's fine. I mean,
All right, let's remove normed and see what happens. That's the best way to learn, isn't it? Okay, so ideally what you're doing is you're plotting a histogram of all of your samples. Okay, that worked. I don't know if it worked correctly. You're plotting bins, and you're plotting, what is 1 over sigma NP? Okay, this is the Gaussian, like that. This is the generalized form for a Gaussian distribution, like the probability.
Oh, you know what I think they were trying to do? I think they were trying to normalize the values from X
To be between 0 and 1.
Yeah, because I think this next line gives you normalized, a normalized Gaussian distribution.
Yeah, okay, that makes sense, because the red line shouldn't be a flat line. It should be a curve that follows this distribution. Yeah, okay, that makes sense. And then you plot bins.
Or you're outputting bins.
Is this computationally intense?
Bins. Where's bins? Okay. So bins is something that
that we changed.
Plot.hist is going to output. Okay, I see.
Yeah. But it's not doing it.
Okay, maybe just stop it.
I'm gonna stop it.
Yeah.
Oh, it won't stop.
Oh man.
Okay, well that's the end of that. But we basically we kind of know what should have happened, but it didn't.
Yeah.
So I'm not sure what this should have been if normed wasn't an option. Like, how is normed no longer?
Try that.
I don't know how to get that.
I think they just removed that parameter. Can you try density? Put density is equal to true.
Oh wait, I think this was just true.
I was just trying to read it up. I don't know, but
Oh wait, hold on. I know what's up. Okay, I need to reinstall. So when you interrupt the runtime, that basically means that you need to rerun the plot, like the numpy, like the import statements. All the packages are not installed. Oh wait, I might rerun these because. Ah, there we go.
There we go.
They changed it to density. Yeah, check it out. So now bin should work. There we go. Okay, yeah. So this is showing you now the normalized like individual distributions. Like we have, I think, how many bins did we go for? 40 bins. So this is 40 values that represent the x-axis. Like the
represent the x-axis.
Yeah, so this is like all of the different small buckets that make up these, like the history.
Oh, okay. So like for example, like the first bucket is negative 3.07 to 2.9.
Exactly. Yeah.
Okay.
Yeah, and so then the red curve represents the overall distribution that you're seeing, which is a normal. Yeah, so basically SciPy, man, and NumPy, SciPy, you can do a lot of really cool stuff.
Yeah.
Yep, pretty sick. So that's my lecture.
Okay. Very good.
Cool.
Okay, let me stop recording.